Hello, AP Chemers. We're going to start Chapter 17 today, which discusses aqueous equilibria, also known as buffers. But actually, Chapter 17 is divided into three parts. The first part is buffers. Then after that, the second part is titrations. And the third part is solubility equilibria, or KSB. So we're going to start with buffers. And before we talk about buffers, we're going to talk about something called the common ion effect. That's where you have two substances that have a common ion between them, and you add those two together. For example, let's look at if we have a weak acid and its salt. So an example of a weak acid is HF. A salt that has the same ion as the weak acid would be something that has F- in it, so something like NaF. So this would be a weak acid and its salt, meaning that it has the ion from the acid. So let's say you take these and you put them both in water, and so the HF, since it's weak, it partially dissociates. You have an equilibrium to form H plus and F minus. We know that the Ka expression for this is going to be the concentration of H plus times the concentration of F minus over the concentration of the HF. So let's say that you take that HF solution, aqueous solution, and then you add some sodium fluoride to it, a salt that has a common ion. And so NaF completely dissociates, since it's a soluble salt, into Na plus and F minus. So there we see that there's a common ion. There's F minus here, and then also F minus there. Now when you add the NaF and it dissociates into these, the sodium ions don't really do much. They just sit there as spectators. But the F minus will contribute to this equilibrium because we're adding a common ion. So we're adding a product. Well, if you add a product, which way would this equilibrium shift? It's going to shift to the left to make more of that HF and use up some of the extra F minus that I have, and also use up some of the H plus. So let's write that down. The addition of F minus shifts the equilibrium to the left towards the reactant side. So let's look at all the concentrations in my reaction here. Let's start with the H plus. So since I am shifting my reaction to the left, I'm using up some of the H plus, and so that's going to decrease. Let's look next at the HF concentration. So we said that the equilibrium is shifting to the left side to make more HF, so my HF concentration will increase. And then my F minus concentration I am adding F minus, and so yes, I'm going to shift to the left to use up some of the F minus, but not all of it will get used up, and so the F minus concentration increases since I'm adding more of it. So that would be the effect on the equilibrium position and all of the concentrations of the species. What about Ka? What happens to the value of Ka? Well, remember that the equilibrium constant is a constant unless we change the temperature. The temperature is the only thing that's going to change it. So what would happen is this number goes up, this number goes down, the H plus. This number goes up, and this number goes up. The way that they increase or decrease will cancel each other out so that Ka remains the same because it's a constant it remains the same at the same temperature. So Ka remains the same. So another effect that we'll have is on the pH. So what do you think would happen to the pH? Well, the pH is the negative log of the concentration of the H+. Let's take a look at what's happening to the H+ concentration. The H+ concentration is going down. It's becoming less acidic. And so my pH would increase. Go up, meaning that's becoming more basic or less acidic. So adding a salt with a common ion to an acid will decrease its acidity, and so it will increase the pH. Next, let's try the opposite. Let's try a weak base with its salt. So a weak base, an example of that is NH3, ammonia. And so a salt that contains a common ion would be ammonium nitrate. So let's look at the dissociation of our base first. It's a weak base, so we have an equilibrium. You can maybe add H2O here if you'd like. And that would form NH4 plus and OH minus. And then if you add the ammonium nitrate, that is a soluble salt. So it dissociates 100% into NH4 plus and NO3 minus. And so here we have our common ion. Both are giving off NH4 plus. So let's look at how that would shift the equilibrium for our ammonia here. So if I'm adding more NH4 plus, the reaction or the equilibrium will shift to the left again. So it would produce more ammonia, use up some of the extra NH4 plus that I added, not all of it, so that would still increase. It's also going to use up some of the hydroxide ion. So let's write that down. So your NH3 concentration, well, let's say the equilibrium shifts left. Our NH3 concentration would increase. Our OH minus concentration would decrease, again, so it's shifting to the left. And then our NH4 plus would increase because I'm adding more of it. Yes, it does shift to the left, but I did add more of it. Not all of it would get used up, so it's going to overall increase. Let's look at the effect on the pH. And so my hydroxide ion is going down, so it's becoming less basic, and so my pH would go down since it's becoming less basic. So adding a salt with a common ion to an acid makes it less acidic. Adding a common ion to a base makes it less basic. Now we had a similar chart to this one right here on our last chapter. We had most of these on here, and so we said if I'm going from most acidic to most basic with neutral in the middle, so the most acidic would be, again, if these were all the same concentration, would be strong acids, the 6 strong acids. Then if I have weak acids, we're going to add this now. So if I have a weak acid with its conjugate base, meaning really a weak acid with its salt, like for example, an HF is a weak acid, F minus would be its conjugate base or its ion or its salt. So if you have a weak acid and its conjugate base or a weak acid and its salt, that would be a little bit less acidic than if you had just the weak acid by itself, because remember, it drives it to the left, making it a little bit less acidic. Then you'd have the salts, so you'd have the acidic salt, then the neutral salt, and then the basic salt. And then on the basic side, the most basic would be the strong bases, followed by weak bases, followed by weak bases with their salts, or weak bases with their conjugate acids. That means the same thing. Like, for example, NH3 and NH4Cl. So the NH4 plus would be the common ion there. So those would be a little bit less basic than weak base, but more basic than a salt. So this chart kind of is helpful to determine acidity and basicity of different substances.